Welcome back, explorer. You're watching Infinity Beyond, and tonight we return to a world frozen in time, but poised on the edge of transformation. Earth, once sealed in ice from pole to equator, was about to awaken. But how does a planet locked in such a deep freeze find its way back to warmth? It begins not with sunshine, but with volcanoes. Even beneath kilometers of ancient ice, Earth's geological engine never stopped running. Tectonic plates continued to move. Volcanoes, many hidden beneath the surface, kept erupting. And with each eruption, they pumped carbon dioxide, CO2, into the atmosphere. In normal conditions, this CO2 would be scrubbed out of the air by weathering rocks and rain. But during Snowball Earth, those natural cleaning mechanisms were shut down. There were no rivers flowing, no soil cycling carbon, no forests to absorb it. So CO2 built up, slowly, steadily, relentlessly. Over millions of years, this greenhouse gas accumulated in the atmosphere. Eventually, the concentration reached a tipping point. Estimates suggest CO2 levels during the thaw reached 350 times modern levels. That's nearly 10% of the atmosphere, a staggering number. And with such intense levels of greenhouse gas, the planet began to warm. The ice didn't melt gently. Instead, the thaw likely came suddenly in geological terms. As the greenhouse effect kicked in, global temperatures skyrocketed. Models suggest an increase of up to 50 degrees Celsius in a relatively short time. The frozen oceans began to crack, melt, and release their own greenhouse gases, methane in particular, intensifying the warming further. And then came the rain. For millions of years, Earth had been parched. When the ice began to recede, rainfall returned with a vengeance. The atmosphere, saturated with CO2, created acidic rain, strong enough to rapidly weather exposed rock surfaces. This chemical weathering absorbed CO2 from the air and dumped it into the oceans. There, it combined with calcium to form carbonates, which settled to the seafloor as cap carbonates, the smooth rock layers we discussed in Segment 3. This marked a dramatic reversal, from a planetary freezer to a global sauna. But the consequences were not just geological, they were biological. Life, having endured in hidden refuges for millions of years, now had access to sunlight, nutrients, and a freshly oxygenated ocean. The floodgates of evolution opened. What followed was nothing short of a biological renaissance. Some scientists suggest that this post-snowball period set the stage for the Cambrian explosion, which occurred about 50 to 100 million years later. During this period, life diversified rapidly. Complex multicellular organisms appeared. Animals developed skeletons, sensory organs, and mobility. The tree of life branched in all directions. Why did evolution suddenly accelerate? Because the environment changed so drastically. New habitats emerged. Nutrient-rich runoff from melting glaciers fueled algae blooms in the oceans. Oxygen levels rose. Food webs became more complex, and life, once confined to the shadows, now surged into the light. But the Great Thaw came with risks. Runaway greenhouse effects likely caused superheated climates, acidified oceans, and mass die-offs. The weathering of rocks removed CO2 over time, but initially, the transition would have been volatile. Earth swung from deep freeze to heat wave, a climatic whiplash that reshaped the planet. Interestingly, this pattern of glaciation followed by greenhouse may not be unique. Similar cycles may have occurred twice during the Cryogenian, as geologic evidence indicates. And the mechanism, CO2 buildup followed by rapid melting, could help explain the climate dynamics of other planets too. If Mars once had active volcanoes and a thicker atmosphere, perhaps it too went through snowball and greenhouse phases. The same could be true for Earth-like exoplanets orbiting in tight, unpredictable cycles. Snowball Earth is no longer just a theory. It's a climate model for entire worlds. And that's what makes it so relevant today. Our current climate crisis involves the same carbon dynamics, the buildup of CO2, the risk of feedback loops, and the unpredictability of planetary systems. Studying Earth's deep past is not just a history lesson. It's a warning and a blueprint for understanding the thresholds we must not cross again. Imagine standing on a rocky plateau in Namibia, holding a stone that once lay beneath a glacier and then beneath a flood of tropical seawater. That single rock carries the memory of a planet reborn, frozen, thawed, and alive again. Earth's ability to recover is extraordinary, but it comes at a cost. Life today thrives because of what life then endured. The scars of Snowball Earth remain written in stone, in sediment, in isotopes, and in the DNA of creatures that learned how to survive, adapt, and evolve. As we close this segment of Infinity Beyond, we leave you with one final image. A world once frozen, now teeming with possibility. It reminds us that even after the darkest winters, spring does come, sometimes in the most unexpected ways. In our next episode, we'll explore the cosmic implications of Earth's Great Freeze. Could alien worlds, frozen and silent, also harbor life beneath the ice? Stay curious, stay warm, and keep exploring with Infinity Beyond.